So good morning, guys. Can you hear my voice?
Yes, miss.
Yes, miss.
So, do you have any question for chapter 4A ALU? Guys, for Segi Penang and Segi TL, have you take a look at the video? Because today I'm going to continue the of memories inside ALU. Because my aim for today is I want to finish the chapter 4 and cover for chapter 5. So inside ALU, okay, we have storage known as memories, right? So these memories can be divided into two parts, which is internal and external. Okay, so SCSG already done their research saying that we have internal and external. We have primary, secondary. Okay, so this would be considered as secondary plus tertiary. Okay, so internal we have RAM, cache, sequential access, virtual, and ROM. So I hope if you watch the videos, okay, you will be able to find all of this information. Because this would be the class activities that I do with the SCSJ student last. Okay, so the tertiary would be your cloud memories or cloud storage lah. Okay, so cloud storage, it can be your Google Cloud, OneDrive, uh, iCloud, and so on. Okay, so let's go for the external DRAM. Okay, so DRAM stands for Dynamic Random Access Memory. Okay, it is a trade speed for size, where you're going to have a large array of slow cells where we will go back to the platform 0. So platform 0 will covers for your physical devices. Okay, capacitor, almost like a mobile phone battery, only tiny CMOS transistor. It can be charged in few nanoseconds, but slow. Okay. Discharge all by itself in a few milliseconds. Charge 1, discharge 0, 1 bit info capacity. To use as memory needs to recharge if at 0. Or redischarge if at 0. Okay? Every 1/50 of a second, an eternity of in the computer world. So I want you all to go and Google what does the DRAMs looks like. I give you 2 minutes to find out how was the DRAM looks like. Okay, guys, have you find out how does the DRAM look like? Okay, let's have Junior. Can you share the pictures? How does the DRAM looks like?
Okay. In the chat, miss.
Where?
In
Where
the
do you share?
in the chat, is it?
You can do your screen sharing also. Never mind. You can do your screen sharing.
Can you see my screen, miss?
No.
Uh, uh,
Try to reshare again. Yeah, no, it's okay. Okay, others, did you get the same images like what Junior did?
Yeah, miss.
yeah.
Okay, now, beside DRAM, what else the type of RAM that you can have? Did you check?
SRAM.
What RAM? Okay, who mentioned the answer just now? SRAM. So, Aaron, did you check about SRAM? How does the SRAM look like? Aaron.
Wait,
While waiting for your friends, others, can you check what is the difference between SRAM and DRAM? Put the differences in tables using a simple key point. Okay, thank
can you
you.
see?
So, when you look at the pictures between DRAM and SRAM, what do you think the differences between them? Hmm.
Mm, One has
One has
more memory cells.
more memory cells.
One,
Oh, what else?
mm, size.
Size. Okay, so it will be one of your homework. Okay, so I want you to find out between SRAM, DRAM, and SRAM, SDRAM. Okay, so what is exactly SDRAM? Do you ever know what is SDRAM? So I want you to find out these three things differences, and then I want you to find out about ROM, EEPROM, what else? Flash memory. Okay, so next, thank you. I will take back the sharing. Okay, so DRAM constructions. Example, you have 4 times 4 equivalent to 16 cell chip. Okay, so where is the cell chip? This one. Okay, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. 1, 2, 3, 4. 4 times 4 is 16. That's why they said you're going to have 16 cell chip. It is real transistor that are symmetrically. Okay, when your gates is open, it will act like your wired. So row select open your transistor, your multiplexer, which is 4 bit. Okay, it will position to 0. Can you see my screen, guys?
Yes.
Yes.
Yes, I confirm, eh?
Yep.
Okay, and then we're going to have capacitor, okay, ampere, latch, and you're going to have your latch on. Multiplexer will be positioned to 1, so output of your latch will be recharged or discharged or redischarged, depends on the row according to your data. So instead of you writing 1-3 above, latch will be new, where the value into the latch will be 5 to 6, which is the same. Okay, this for this understanding, I will share you a YouTube link for you to take a look. And I want you to provide me information. What do you understand about this? Okay? Wait a minute. Okay, so let's continue with the DRAM inside your logic sim. So simulation of the whole system, not a single chip. So there we don't have time to discuss about the memory architectures. Okay. So if you want to find out more, you can Google by yourself. Okay. Signal cell if down, D would be called disconnected and your chip will be offline. So if the clock memory write happen when a rising age. So LD is latched down is a misnomer, mean that your memory is reading. If up, if down, the memory would be writing. Okay? Clear, it means that CLR would be means by clear. Erase the memory once up, irrespective of the clock. Okay, so A would be your address bunch. D would be in and out terminal. If your LD is what is that symbol? Anyone knows what is this symbol? Guys, anyone know what is this symbol for? Hello?
So which one? The one in front of cell?
Yeah.
Is it and?
And okay. So LD, if LD and cell, okay, D will be asserted with the content at the address. Okay, but if LD prime, LD prime and with your cell, the data is remembered at the address. A would be the next at rising age. Okay. So far here, do you have any question?
No.
Confirm, eh?
Okay lah.
Okay. Okay. So, as you can see here, as you look at here, so where does this LD, CLR, A, and D are located? Where? Where? If you said just now, you understand, right? So where does these things located? Anyone want to try? Where does this LD, CLR, cell A, and D are located? Come on, guys. Hello? Anybody home?
Yes, miss.
Oh, where does this AD, LDR, and CLR located? Hello? Okay, it's fine. Since he doesn't want to talk, it's fine. So next, ROM. ROM is actually a useful component, okay, where the full name is read-only memory. So the differences between ROM and your RAM is the components that have been illustrated inside your pictures like this. Okay, as you can see, you have your cell, LD, and CLR, also AD. But in your room, you only have AD and cell. Okay, so it will be useful because the content is permanent placed inside the chip, can store your program code, data, or signals. So Logicsim will treat it like a RAM, except there is no memory write, and LD is permanently out. Okay, so the D follows A all the time, no matter what will be the clock is. So it is universal combinational circuits. For any combinational of A, the output D is simply taken from the ROM content. So this would be your input. This would be your output. And below here would be the conditions or what? Or what we know as. Okay, next, ROM implementation. A large decoder could be several cascading ones plus a wire grid. Okay, decoder decodes into one or disconnect. Usually they will use ordinary decoder plus control buffer. Okay, each of the intersections is diodic and conduct only west to south. Okay, initially intersection points are welded. To place content in the room, okay, once burn out the unwanted intersection, it can be done by the customer applying more than standard CMOS voltage and short circuit output. So what is CMOS? Anyone know what is CMOS? No response also. Okay. Okay. So three decoder,
Is
we
it
have
conductor,
huh?
semiconductor, CMOS?
Sure, sure. What
Uh,
is other things than CMOS? Huh. Besides CMOS, what do we have? I have mentioned it before. Hello. Sanet?
Yep, miss.
You said CMOS is a semiconductor. So
Ah.
is there any other things than CMOS? Any other types?
Uh, oh, you mean you're asking me like, is there any other type of semiconductor?
Mm.
I'm not sure.
So it will be your homework also to find out.
Uh,
Okay. So this would be the 3 decoder where we already studied it before. Okay. So it could be a higher fan out to reduce the number of decoder, necessarily 1 to 4, which we're going to have 21 decoder for 64 cell. Okay, still we need n to the power n divided by 4 decoders to find for the n memory cells. Okay, therefore it will be having too many what? What do we going to have? So for example, if we have memory cell that's equivalent to 126, how many decoder that we have? So 126 will be divided into 4. How many that we will get? Okay, so let's proceed to the next one. So this is the matrix decoder. Okay, so 4 plus half, it will become 5 decoder only. Okay, so but then you're going to have around 64 AND gate as extra. Okay, so calculations for 3 decoder, you're going to get 1 plus 4 plus 16 is equivalent to 21. Okay, matrix decoder 5, 2 to 4 decoders and plus with 64 AND gate. So the questions, 16 extra decoders or 64 AND gates, which one will be better? So 2 to 4 decoder requires 4 on 3 input and gates, 4 times 3 input and gates, and 4 NOT gates, where at least you're going to get 50% more transistor. But then this calculation is tech dependent. So we need also to check the other factors, for example, wire length, regularity of your pattern. So it can be more than one solution available or required to be constructed. Okay, so you can do the quantitative analysis by checking the length of wires, regularity of the patterns, and so on. Okay, so flash memory is your EPROM. Okay, slow write, fast read, halfway between the RAM and ROM. Okay, so key storage technology for mobile computing. So mobile computing, everyone knows, is your smartphone, your photos, your photo and video cameras, your IoT, and for currently is your tablets and your also your laptop. Recent not available in 20th century, but the principle is already invented as far as 1970. But first commercial product is on 1987. Okay, so the key device, floating gate transistor, we have MOSFET, and we have floating gate transistor. Okay, So can you see the differences between these two things? Okay. So one we have a floating gate, the other one we don't have the floating gates. Okay. So as you can see here, two charge state 1 bit per floating gate transistor. When bit is equal to 0, the negative will be the charge. But if the bit value is equal to 1, it will be a no
No charge.
charges. Okay. If you to find out more about this, okay, I want you to find okay, so I want you to go and do some research on the link that I will share it to you later. Is about these figures. Okay, so I want you to give your insight about this once you read and watch the videos. Okay, so next, this is the reading part. Your voltage T0 will be bigger than voltage T1. Okay, when your bit value is 0. Okay, so the principal blocking the N transistor gate. As you can see, the graph producing different voltage for each of the transistor gate. Okay, so this is the writing method when you are writing 0. So this is the erasing methods for the using the tunneling. Okay, so limited number of write and erase cycle. Injection through the oxide damage your oxides. Tunneling through the oxide damage is less. Okay, it will up to 100,000 cycles then become useless. Therefore, your oxide layers will fail to trap the charge. If used for random access storage, it must be even out of your load. So this is the multi-bank memory system, which is your RAM. So this would be the how was your bit slice memory looks like. Okay. So alternative register implementation, it will known as an abstraction. Like we have built a register from gates. So you will work with any platform zeros, okay, your hardware lah, which involve with your CMOS, ECL, PTL, optics, and anything that implements your gates. Okay, correctness of behavior does not depend on your platform zero, but the cost does. So CMOS cost characteristic, first thing is your number of transistor, and then you cover for your speed, power, or heat. So is it possible for us to achieve better cost directly from the transistor? So this one also what would be one of the questions that I want you to go and do some research. Okay. So for up until here, do you have any questions you want to ask? Do you have any question, guys? So this would be the sequential logic between D latch and MS D latch. Okay, so I give you 10 minutes break, okay, before we proceed to the chapter ALU for B. Okay. So let's have a 10 minutes break. Okay, so let's proceed with chapter 4, ALU. Interest. So, this is the example. ALU actually is a combinational circuits where you have four inputs, where four inputs can be divided into few components, which is two operands, one function for operation, and two C in. Okay, you're going to have two C out, result, and CV and Z. So what is CV and Z? What is CV and Z? Anyone know? Hello?
Is it the flags?
Okay, so the flags, what is the full name of the flag?
Carry? Carry flag?
Carry, okay, then
Overflow?
overflow,
0
zero,
and negative?
negative. Good. Okay, so this one can drive for bus 1. Always slash result in RR. What is RR? RR can assert on bus 1. Okay, the next cycle. So this is the overview. So your memory operation can be read, write, or none. Okay, so you have index 0, assert 0, index 1, assert 1, index L, and latch. Okay, so you're going to have your general purpose register, you're going to have your bus 0 and bus 1. Okay, so memory interface, you're going to have some memory operation where operation can be 3. One is none, write or read. So if none, it means it is being disconnected and disabled. If right, the address from bus 0 will latch. The data will latch from bus 1. Again, when you read the address from bus 0, the data will assert onto your bus 1. Assert and latch will be different. So what is the differences between latch and assert? What will be the differences between latch and assert? Hello. Okay, it's fine. So next, we're going to see about the control. Okay, PC is your program counter. IR is your, what is IR? Anyone know? Huh. No,
Nope.
no. Others?
Not sure, miss.
IR is your instruction register. How about your PS? PS? This PS is not personal status, eh? This one known as processor status, which locate your flags. Okay, so PC is your program counter. Okay, where the special purpose is to register and hold your addresses for the next instructions. Okay, while for IR, your instruction register, okay, it is to hold the current instruction, while for PS, they hold the latest effective flags. What is flags? Huh, what is flags?
The CVZN?
Oh, okay, what else?
Bit. Specific bit.
Okay, what else? Anything else? No? Okay, thank you for answering my questions. So those who did not answer, did you understand what is happening here? Hello? Is you guys alive? Hello, still alive? I have one more chapter to be done for today.
Alive means alive.
Alive, eh? If you does not alive, I give you 2 minutes to take your oxygen. Is it enough? 2 minutes for you to take your oxygen? Okay, take a 2 minute break, take your oxygen, and come back alive. So, are you guys alive after 2 minutes break? Did you take enough oxygen? Or you just a robot, came into my class, idling because you doesn't want to do anything? Okay, so let's proceed. So sequential instruction execution. So instructions are fetched from memory one by one. Okay, so instruction will sit in your IR for one or more clock cycles. So your cycles will be named as fetch, phase one, phase two, next, and the next cycles. Okay, until the things is finished. Okay, so you're going to have your sequencer. So sequencer actually is a part of your instruction machines that create the control pulses. For example, your fetch, your phase one, phase two, and so on. The number of phases depends on the instruction itself. Okay. So the sequencer is actually a part of instruction machine. So the rest of instruction machine is purely combinational, which is analogous of your ALU, which is your CU. Okay. So this is the architecture of the instruction machines. Okay. So this one is your homework where you need to explain in your own words how was this architecture being used for your instruction machine. Okay, all of you alive already, right? So already take your oxygen, so you are not sleepy, right? So it shouldn't be problem for you to find this information. Okay, I will screenshot this one, put in the chat box, and it is a homework for all of you. Okay, and you can discuss with your lecturer during your class. Okay, so next, this is the complex design space where you're going to have a plenty of threads of where it will covers for speed versus real estate, okay, and then will versus the powers. Okay, and then programmable. Okay, efficiency of your machine instructions, the body of knowledge or computer architecture. From year two, you guys all the way to the PhD jobs in the Silicon Valley, we limit ourselves to interesting two interesting questions that to get a little of taste. Okay, so operation code problem. So memory organized as in array of word in a fixed size L, typically 32 or 64 bits. Okay, so fetch logic will fetch the instruction in one word. Okay, there will be a fixed number 2 to the power of R of your GP register. So usually, typically 16 to 64, where your R would be 4 to 6. Okay, so did you understand this statement, guys? Hello? So 2 to the power of R is equivalent to your bit size. For example, you have 32 bit. 2 to the power of R would be 2 to the power of what? Hello? 4. So we cancel 2. We're going to get R is equivalent to 4. So this is proven. So some instruction require 2 register, 1 register, or no register. So how to divide? So we will use these things. Okay? So next, 2 methods. We're going to have our waste space. We have our opcode, Rn and Rm. Okay, where opcode will have 6 bit. Register number would be your 4 bit each. Okay? So this will be your opcode, only 6 bit. How come here is 5, but here they mention only 6 bit? Anyone can explain?
Does it include 0 also?
You have to include 0, okay? What else?
Extra space not needed.
Oh, extra space. Okay. So register number 4 bit each. 4 bit each. What does this mean? 4 bits each. So if RM or RM and RN not required for OP, ignore. So you're going to have your prefixings. Okay, the beginning of opcode is 9 bit. It's not equivalent to your opcode 9 bit. Okay, so the beginning of opcode will not equivalent to your opcode like this. Okay, it will be different. So this one and this one is different. This one and this one also different. It does not mean the same thing. Okay, so as you can see here, that's why previously you need to know about the binary values. Okay, so if they start with 0, it is only have 32 instructions. If you have 1 0, you're going to have 2 5 6. 1 1, you're going to have 4 0 9 6 instructions. Okay, so far so good. Do you have any questions? Do you have any argument with me for this one? Hello? Okay,
No,
so
miss.
let's jump straight off. We have 2 methods. Method 1, okay, fast determination of your output, which is your decoding. Information capacity wasted. Fewer instructions are possible. But if for method 2, slower decoding, where you requires to determine your prefix, only then you can identify your default code. So information capacity will be utilized. Okay, so it's going to have an issues when we involve about the memory. So we're going to use the case study of chicken and egg problem. So to write or read your memory location, it has to address to be asserted on your bus. So the address actually is a number that has to be inside your register, but the number have to come from somewhere. From where? Is it from your memory cell? Then if it is from your memory cell, okay, you need to address, okay, of the cell. Okay, so therefore it will back to square one. So who will create these numbers? Okay, so one address is always available, which is PC. What is PC? Do you remember what is PC? So PC is your, hello, PC is your what? Program counter. So the address of the next word of the instruction has been fetched. Use that word for your data immediately required to the instruction. Immediately means that before any instructions the instruction is supposed to do. So this is known as immediate operand. A whole machine word could be any number must increment the PC again before the instruction being terminated. Okay, that's why your PC will always keep on changing. Okay. So for example, LDI, it means that load immediate. So your PC count will put, and you will have your code for LDI. You're going to put it in the R3. So this will be your code. So once your instruction decoded, it's about be executed. So your R3 will contain the binary bit. Okay. So now use your R3 to read your data from your memory. Okay, where the cell number is 0 times 6F. So far, do you have any question? So how does 06F is being calculated? You know? So how does this 06F being calculated? Hello. Still remember the conversion that I teach you? Guys, I need your response. So the 0 times 6F is came from your bit here, where we need to separate them into two octet, where 6 is from 0110, F would be 1111. How do we get 1111 become F? Here you need to use the formula 8421. So you're going to get your F. Same goes with this one. 8421. So 4 times 1 plus 2 times 1, you're going to get your 6. Okay? So this will be the summary. So this is your ALU main architecture, where you're going to have your input-output devices and you're going to have your central processing unit. So ALU would be inside your CPU along with your CU and sets of register. Okay, so register can be your program counter, instruction register, memory address register, memory data register, and general purpose register. Bus, we're going to have 4: address, data, control, and power. Okay, so this one you can memorize like C pack. C is for control, P for power, A for address, D for data. Well, for this one, you can memorize it like PC will have your IR, where IR going to have your MAR and your MDR. Only you're going to have your GPR. Okay, this is how you memorize the register and bus. So bus going to have 3 types of organization, 1, 2, and 3. So this is how does the bus looks like. Okay. So I want you to identify what would be the differences between 1 bus, 2 bus, and 3 bus. Okay, so we finish our chapter 4 and let's have a 15 minutes break before we go in for chapter 5. Saya punya ada. Tapi macam hauk sikit lah. Dia hantar ikut dan dia. Saya suruh hantar yang final draft, dia tak hantar. Dia final submission dia tak hantar. Dia hantar first draft je. So dia dapat makan untuk first draft je. Presentation pun hauk. Okay, let's proceed for chapter 5. Okay, the survey of the rest of the architectures. Okay, so tenable models, you already learned, we have 5 levels. Okay, so now this is the components of your computer where you have input, your output, your ALU, and your memories. Okay, so this one is the section of your memory. So this one will be the sections of your CPU. This one is your output, and this one will be your input. Okay, so what would be inside your level 2 platform? Okay, so just now I already mentioned you have your CPU, memory, bus system, and also your clock. So a CPU actually is a scratchpad where there will hold temporary workings register. They will perform the FDE, fetch, decode, and execute engine, where a sequence of instructions, okay, which undergo for CU, ALU, manipulating your data items, logic circuits, selecting the memory cell and copy the bit string between your memory cell and register. Okay, memory organized as a set of n-bit memory cells, each of which is labeled by known as your address. Okay, a bus system connecting your memory and input-output devices to your CPU. A clock synchronizing your operations. Okay, so CDM 8 platform 2. So 8-bit level 2 platform, you have your CPU memory, no input-output devices inside your basic system, and clock will synchronize your operations. Okay, so CPU, they will have the data being manipulated in 8-bit chunks. Mostly will be 8-bit instructions. While for your memory, you're going to have your 8-bit memory cell and 8-bit addresses. So maximum, you're going to have 256 memory cells. Okay, so this would be the CDM simplified overview. Okay, you're going to have your PC, PS, IR, along with your CV and ZEC for your flex, CU, memory, and also your ALU. Okay, so as you can see here, so this is the illustration of the So until where that I have talked just now, I think I've been kicked out from the meetings. I'm not sure why.
I think the slide after this one,
The slide after this one.
the platform, the CDM8 platform 2, the slide after that one.
This one.
Yeah, this one.
Oh my god. Okay. Wait, Okay, so this one would be the illustrations of the same actual architecture that I have shown previously, like this one. Okay, so it is representing this into this kind of representation where you're going to see the addresses in the bit value. Okay, so you take a look at the clock here. So this is the clock. Okay, this will be your CU where you're going to have your, inside your CU going to have your PC, PS, IR. Okay, inside your PS you're going to have your flags. Okay, and then you're going to have your scratch pad, which have your registers, ALU for your arithmetic logical operations, and then you're going to have your memory. Okay, so this one would be your real illustration using logic sim. Okay, using logic sim. So the one that being highlighted here, you're going to have around 1, 2, 3, 4, 5, 6, 7. So we're going to have 7 components where some of them we already learned. Okay, for example, the data bus we already learned. We have 3 types of organization. Okay, we have ALU register and ALU. Already look about the carry, look ahead. We already learned about register, we learned about shifter and also your instruction decode. So all of this we have learned previously in a previous chapter. So I hope you can do some conclusion about why does all of this are required to be learned in this subject and how was all of this being used in our life. Okay. So next, CPU is a central processing unit where all of them is a functional units. Okay, so this one is what we said, a more simpler illustration for you to understand. Okay, so this one is the zoom in of your this chip pictures. Okay, so inside your memory unit, so this MU is your memory unit. So inside your memory unit, you're going to have your PC, IR, MAR, and ER. Okay, so inside your ALU, you will perform your calculations. So you're going to have your CU here. This is your buses. Okay, and then you're going to have your cache memory and also your register. Okay, so inside your CPU, you're going to have few things, which is register. One of them is register. So CDM CPU contains small numbers of register where your register will act as your memory cell, but typically implemented using different technology where it will be much more faster. Okay, even though it is faster, but it will be very expensive. Okay, so they are physically internal to a platform CPU, so they are not referenced in the same way as your memory cells. Okay. They are capable of supporting operations that cannot be performed upon your memory set. So registers typically characterized by two things based on their size, where we calculate in bit, and the purpose, what they are being used for. Okay. Next, beside register, we go and take a look about our scratch pad. Okay, this scratch pad is a for general purpose register. Okay, where each of your register hold 8-bit string. So if we have 4 GP, it means that we're going to have 32-bit in total. Okay, so GP register are used as a temporary storage area for data item. For example, your numbers, your characters, and your addresses, and so on. So they play in a direct part in computation because CDM8 level 2 platform can only perform operation on bit string that held inside your register. Okay. So GP register being numbered 0 to 3, and we will use the name of R0 until R3 to refer them. So the register that I have mentioned just now is actually your general purpose register. These R0 until R3 are reserved, cannot be used for other senses, where it will help that this register would not be confused with others. Okay, so next, inside your CPU also you're going to have your CU, where this will orchestrate the fetching from your memory, decode and execute your instruction. Usually it will read and update your PC register. Then only they will load the instruction to the instruction register, decode them and tell your ALU and other parts of the CPU what to do and when to do it. Okay, it makes the use of CV and ZAC flag in the processor status register to test whether the condition has met or not. So these things, this sequence, I want you to really understand and can relate, because later you will use this one for your analysis. Okay. So program counter with an instruction can be executed. Your CPU's control unit need to fetch it from your memory. To do this, memory address of your first byte of the next instructions. Okay, so usually this addresser will be held inside your PC register. Okay, so the PC always contains a pointer to the next instruction, where the PC must be modified each time an instruction is being executed. Okay, so usually when your instruction will be executed, next can be changed by modifying the addresses inside your PC. So CDM8 has 8-bit program counter. So usually this instruction register will be hidden, okay, to the programmers, but we know it is that. Okay, so inside AIR will have bit string, okay, where it will represent the instruction that being executed right now, that is currently executed lah. Any bit string of your write line can be interpreted as an instruction. Whatever the bit string is loaded into the instruction register will be treated as instruction to be decoded and executed. Okay, so usually the stored bit string are used as instructions, and which are used as data depends on when they are held inside your memory. Where is the location lah? Okay, so next is your PSR. So PSR is used exclusively to manage conditional for computation. Okay, so it tells what happened when the last time you use your ALU. So usually you're going to have your 4 1-bit flags, which is CV and ZAC, each of which indicates something about the result of the most recent operation performed by ALU. So the pattern of flags can be used to determine whether or not a specific condition was met by most recent ALU. So these may be used to decide which instruction should be executed. For example, which we use the if statement, while statement, for statement inside our coding. Okay, so this would be the 4 processor status flag. Okay, as Aaron mentioned just now, C, okay, is for the carry out. V for overflow, N for negative, Z for zeros. Okay. So why do we need register? So register technically is just more memory. Why we need to have them? Okay, so we can use our main memory for everything, but if we want it to be faster, it will be much more expensive. So the platform needs circuitry to connect it to the ALU to every memory cell, which will cause it much more complex. By restricting your ALU operation to a small number of GP register, we can represent the instruction in a shorter bit. Okay, therefore your machine code program can be smaller. When it is smaller, it will be simpler. Okay, so the PC, the PS, and the IR need to be in a fixed location so they can be fast. Okay, so that would make sense to put them inside your CPU. Okay, so we go for ALU. ALU is the computational engine of your level 2 platform. It performs various functions. For example, your arithmetic operation, your logic operation, your manipulation operation. Okay. So what does your ALU do? They manipulate the bit string copied from your GP's register. The result are copied to the GP register and used to modify the flags in the PS register. But it cannot remember your result, copy your data or to or from your memory, control which and when instruction to be executed next, and what will be performed. Okay, it is not a platform that have their own rights. However, it is important the component of the platform. It is very important, okay, to have ALU. Okay, so this is the memory cell. How does it looks like? Okay, so the level 2 platform have a memory comprising a collection of memory cells. So this overall we know as a memory, but when we look into one by one, like this known as memory cell. Okay, each of the cell will contain of 8-bit string, which equivalent to 1 byte. Okay, so each of your memory cell is going to have 8-bit, which is equivalent to 1 byte. So no memory cell can be emptied. Usually each of them have a bit string. Must. Cannot be emptied. Okay. So next, memory addresses. Okay, so memory addresses where it will be used as a label for each of your of what? Of your memory cell. Okay, so if a platform is to read the bit string from memory, it must store the addresses of the memory that contain the bit string. So if they ask to write, it must store the addresses of the memory site. It needs to be modified. Each address refers to one specific memory cell and indirectly to the bit string it contains, finding the cell known as addressing it or referencing it. If we want to obtain the content, we know it as a dereferencing. So each cell might have their own unique addresses. If two addresses have the same, it means that they refer to the same memory cell. Okay, just like this. This is the example. Okay, if you look at the addresses, it will be different. It will not be the same. Okay, so addresses are themselves bit string. Okay, different address, different memory cell. Okay, so the length of the bit used for addresses dictates the maximum number of your memory cell of the CPU may address. If the addresses is n bit string, we get 2 to the power of n different addresses. For example, I said we're going to have 16 bit. So it means that how many different addresses we're going to have? 2 to the power of 16. So this would be the value of our different addresses. Okay, so it does not mean the platform must have 2 to the power of n, but it can be max to this value. Okay, so in the case of CDM8, addresses are 8-bit string. Okay, so the CPU can address up to 2 to the power of 8, 256 memory cells. So the maximum amount of RAM can be support is 256 bytes. Okay, so this is the examples of your addresses that are in the bit string. So all the addresses are numbers. Strictly speaking, each of your memory addresses is just a bit string which is used to switch on a particular memory cell. Okay? However, we will treat the addresses as they are an assigned number. That's why you previously learned about signed and unsigned numbers. So where each of your memory cell is associated with unsigned number represented with the addresses starting with 0. You are not going to start with 1. It must be started with 0. Okay? So cells with consecutive addresses are treated as though they are organized consecutively in your memory. That the platform's memory can be viewed as an order collection. Okay, this is used when we are storing the multi-byte data such as your character, string, or your program. Okay, so what are these addresses used for? To referring your data item and manage the order in which which instruction should be executed. So when we refer to a data item, it means that each of your data item has their own specific addresses. Okay, they will occupy several contributive memory cell that has a start and extent. The number of cell it occupies. Since programs are encoded as a bit string, they also a data item. So usually a program has a start address. This is where the first instruction are fetched when your program is executed. Execution will continue until the platform is told to stop or you ask them to quit or close. Okay, so managing the order in instructions are executed. So the order is dictated by putting the addresses of the next instruction to be executed inside your program counter. Okay, representing your program, we have seen binary representations of numbers and addresses. How about your program? Okay, so we also need to have binary representation of our program. Why? Because without a program, to follow a computer does nothing. Okay, so everything must be represented using a bit string. It's only the only way that your computer can understand. Okay, so what actually is a program? It is a long bit string made up of machine code instruction. So about this machine code instruction, I will teach you in tomorrow lectures. Okay, and so this bit string is organized as a sequence of bytes, okay, where it will make up a program that must be placed inside your memory so that your instruction can be executed. Like any sequence of bit held in your memory, a program has a start addresses. So when you run a program, it means that you execute the instructions, okay? So when execution is begin with the instructions, okay, the instruction will be held at the start address of the program and proceeds from there one instruction only at a time. You cannot run multiple instruction at one time. Okay, so a machine code instruction is any bit string that may be interpreted by level 2 platform as an order or instruction. Okay, for it to perform a single well-defined action. So different instruction must be represented by different bit string. So the length of the bit string is used to encode the instruction dictates how many different instructions as a platform may have. Okay, just now I already mentioned n bit string is equivalent to 2 to the power of different instructions. Okay, but they are just a bit string. Any bit string that represent a level 2 instruction will have other interpretation in other contexts. Okay, it also will represent a data item in another context that may be interpreted as your level 2 instructions. Okay, so for examples, machine code instructions are just bit string, but they are bit string with a particular meaning. For example, we are having hot. Okay, so when we write instruction, we will use the name to convey something about their meaning. Okay, the first one is hop, add, subtract, move. Okay, so that one would be the instruction. So the halt instruction means that the platform has to stop the clock. Okay, so operation is halt, the operand is none. So no data is required. Okay, so when we talk about add R1 into R2, okay, so it means that this instruction is to tell the platform to perform the addition, okay, from the numbers that is inside R1 with the numbers that inside in R2. Where do you store your information? In R2. Okay, so the operands will be your R1 and R2. Okay, so this R2 would be your storage or your what? Or you will leave the result in. Okay, so next, opcode. So most of the machine instructions specify two things: operations, okay, where it will identify the functional units within the processor will be used and what in what type of orders. One or more data item that will be used by the operation. All instructions that require a particular operations to be performed will contain the same bit sequence in the same position. So this bit string known as your opcode for the operation. So each of your instruction can contain this opcode will cause the CPU to perform the same operation but not the same data item. Okay, so operands contains within an instruction specify what data item will be operated upon. Okay, for example, some operation no need data, some of them require one or more data items, some of them will produce a data item. So operand can be a data item. However, most of the CDM8 operand are referenced to your register. So actually register will hold your data item ready for use or that will be used to hold your data item after instruction has been executed, or a register that contain address in memory from where a data item will be copied or to which data item will be stored. Okay, so this would be the overall structures, okay, where we use the real hardware names. Okay, so identifying your register, it is necessary to include each instruction the identities of any register it will be used. We will assign different bit sequence to identify each of the GP register. So register 0 we know as R1 where it will identify using the bit string 00. Okay, register 1 identified by 01, register 2 10, and register 3 is 11. Okay, so the PC and PS register do not have labels, so we cannot refer them directly. While for IR is invisible to the program, so no label is required. Okay. Next, so instruction, what does your CDM8 machine code instruction looks like? So each instruction is a bit string. Most of the instructions are in 8-bit string. Some of them will be 16-bit. Okay, the first part of your instruction is your opcode. So opcode will be in different length. It can be 4, it can be 6, or it can be 8. So if an opcode is 4-bit in length, there would be a room to specify your GP register as operands without using a second. But longer opcode are used for instructions that do not require two operands or will take up 8-bit value as an operand and will take up 2 byte. Okay, so this would be the example of opcode and their instructions. So opcode is the abbreviation from your operation code, also known as your instruction machine code, instruction syllable, instruction parcel, or your op string. Okay, so opcode is the portion of machine language instructions that specify the operation to be performed. Okay. So far, do you have any question up until here? Okay, so this is the instruction formats. So this is where you need to memorize. You need to use this later on, maybe for your coursework assessment. Okay. So this is how does your machine instruction format when we use the real input values at hashtag 45. So the 45 is your operand. So the output at hashtag, it means that at is your operation, hashtag is the addressing mode. Okay, so this is the opcode and their operand. Okay, so we have 0 instructions, we have 1, 2, 3 instructions. Each of them will have different things. Okay, so this is the instruction with an 8-bit code. Some instructions just have an opcode. So this 1 would be explaining about all of these 4 instructions type. Okay, the first one is an instruction with an 8-bit opcode. Okay, so this one with the 4-bit, each instruction with a 4-bit opcode orders the platform to perform operation that requires 2 GP. Okay, so the opcode will be 0001 refers to the add option. Okay, add an 8-bit data item from one of your GP to the instruction comprise 4-bit opcode 0001 followed by 2-bit string specifying which register to be added from and which register to be added to. So add R1 into R2, it means that you add your 8-bit numbers in R1 into your R2. Okay, so for example, it will encode it like this. So 0001 is means by add. 01 is your R1 value. 10 would be your R2 value. Okay. So LDI operations, it means that load immediate. Okay. So TDM8 has an special operation known as load immediate that will getting the initial values into your GP register. Okay. So the 6-bit opcode 110100 refers to the load operation. Okay, so each code would have different things. 001, it means add. 110100, it means LDI, load immediately. Okay, so if they say add, you use what type of code? 0001. If they say LDI, you need to use 110100 as the code. So this one would be your R2. This one would be your value. Okay. Load your register 2 with bit string 0 It will encode it as like this. So when we combine LDI R2 0B 01110 So when we convert into a bit string representation, it will be like 110100. And then your register is 10. And then you put your value 0111010. So far here, do you have any question? No? So let's proceed. This is the machine codes program. So bit string used to represent the machine code instruction. Some instruction may be longer than others. A machine code is a bit string constructed by gluing together a sequence of instructions and also your data item. Okay, so you can see here, we have different types of machine code program. But the way that they represent themselves would be different. Some of them will be gluing up together with the instruction. Some of them is only with data. Some of them instructions. Okay, so the representation of the instruction also would be different. Okay. So interpreting your bit string, there would no way to tell that what a bit string represents just by looking at it. So any bit string that is right line contain a single complete instruction for a platform may be interpreted as your instruction, no matter what originally we intended it to be. Okay, similarly, any bit string could be represent a sequence of instruction may be interpreted as your program. How does a platform know which bits are a program? So this would be a few questions that you should came into your mind lah. So what makes a bit string into a program? Where is it located? Okay, so you just need to know that put the bit string in the right place, then it will be executed. Okay. So far, do you have any questions you want to ask up until this slide? Hello? Because after this, I'm going, for tomorrow, I will proceed into the FEC, which is the fetch execute cycle. Up until here, do you have any questions? So instruction execution instructions are followed one at a time in a strict sequence. Okay, so bit strings encoding instruction are held inside your memory cell. Copying, we known as fetch. When we working out, we known as decode. Perform action, execute. Execution comments at your startup. So your platform level 2 will start with fetch, decode, and execute your operation from the moment it is being switched on. Okay, so far, do you have any questions? No? Okay, so let's end our class here. So see you when I shall see you. So for SSG, tomorrow our class still online, unless you are requesting to have a physical class, I will. So thank you, class. See you and bye-bye.
Thank you,
Thank you,
miss.
miss.